Good afternoon, everyone, and welcome back from lunch. I hope you've enjoyed your sessions so far today. We have a lot of content to cover over the next half hour or so let's get started. Yes, serverless today is fundamentally transforming how you build applications and how you think about and manage infrastructure. To give you an example, if you were around for the modern architecture track earlier today, you would have seen how you can run map-reduced jobs on Lambda functions. My colleague Uni next door is delivering a talk right now on building a serverless data lake. Traditionally, when you're thinking about big data workloads, you're thinking about clusters of servers. Yet today, a lot of the components of your big data workload could be entirely serverless. However, not everyone is aware of the different architectures when it comes to building serverless applications. So today's talk is really to inspire you about what is possible with serverless. Serverless applications are event-driven, which means there is an event source that generates events, and there is a consumer that processes these events and might optionally speak to other downstream systems in order to do so. You can think of events as anything significant within your business you care about. This could just be visits to your websites, or this could be changes in data state, like someone ordering your product. Event-driven architectures, by their very nature, allow you to build loosely coupled systems. This is because the event source and the consumer need to have little or no knowledge of each other. They're also very responsive when it comes to sudden changes in load. And finally, because you don't have this always-on server behind the scenes, you consume your processing resources only when events occur. Now, on AWS, most serverless architectures revolve largely around AWS Lambda. There are three different ways in which you can invoke a Lambda function. The first is synchronous, which means your caller will wait for a response from the Lambda function before doing any further processing. Examples of this pattern include RESTful API calls. The second, asynchronous, is a fire and forget mode. So your caller does not wait for a response from the Lambda function. Example here could be batch-based file processing sort of tasks. And finally, you have the stream-based mode, which you use in the context of streaming data. Data that is generated continuously or in near real time and is generally processed in batches or in specific time windows. Unlike the first two, this is a pull-based model, which means your Lambda service is continuously polling your streaming resource to pull down the changes for processing. So depending on your use case, you will see one of these three different invocation models in your architectures. So let's look at how some of our customers and partners are using serverless today. The first category is to build web applications. The second is to build backends. This could just be API backends to your mobile or web applications, or they could be backends processing sensor data coming in from IoT devices. The third is data processing. Now, one of the drivers for Lambda functions was the need to attach compute to storage, because we had customers storing large volumes of data in S3 buckets and needed a way to easily process this data. So not surprisingly, this is the largest category of serverless use cases today. If you're building text or voice-based chatbots, you can have Lambda power their logic. Alexa skills are written in Lambda functions. And finally, you can use serverless applications to automate the management of your AWS environment. If you're someone who's just getting started on the serverless journey, then this is a great place to start because applications in this category are relatively easier to incorporate into existing architectures. So on that note, let's kick off our study of architectures by looking at how one of our customers, Global Fashion Group, are using serverless internally today. I feel a bit nostalgic talking about them because I know I met them initially about 10 months back when we were still brainstorming the initial serverless architecture. And I clearly remember we didn't have a whiteboard in the room, and we actually whiteboarded on the window after that. So it's my pleasure today to invite on stage Minh Thuong to share with us what that architecture looks like today.
Thank you, Arthi. Hi everybody. My name is Minh Thuong. I'm working at Global Fashion Group, which is a parent company of 5 e-commerce in the world, specialized in fashion. including Zalora in Southeast Asia, the Iconics in Australia, and 3 others in different regions. In GFG team, we are developing a pricing engine driven by a lot of data analytics to recommend the best pricing for the catalog of each region. The system needs to support up to millions of price updates regularly. However, the traffic is not always consistent, but can suddenly increase due to the bad fits coming from different triggers like competition, inventory, or promotion. Given the characteristic of the product, we decided to apply microservice and event-driven architecture. The idea is to have a common core engine that can support all the regions and an integration layer to integrate with their system. Besides, we want to build a full stack and agile team that can support both front-end and back-end. Also, with continuous deployment and automated testing, we want to push code to production frequently. These are the tech choices that we made based on the product and the team nature. For programming language, we chose JavaScript for both backend and frontend with Node.js and React.js. We also use Python for some machine learning module. For hosting, AWS was a part of our IT strategy for the group and all the reasons. As it comes with AWS, Lambda was selected as the main component to build our microservice. Then, quite natural, we use Kinesis, DynamoDB, and S3 to build up our architecture. What you see here is one of the real feature flow look like in terms of architecture design. So it's quite complex. I will not go into detail here, just want to give you an idea. Let's look at the high-level architecture. Before going to pricing engine, the raw data from external sources will go through our big data platform for cleaning and processing. After that, the event will be sent through Kinesis to trigger the flow. You can notice here, there is one price optimizer service that running on EC2 instances, but not Lambda, because of the long processing tasks that we cannot split. The first service received those events is recommendation, which selects the best prices among multiple price sources and store them in RDS Postgres database so that later they can be retrieved to the API gateway to display in the dashboard where the user can log in to see the recommendation. The user can approve or reject the prices. For the approved price, they can send to validation service where the new updates will be checked by different visit rules that we pre-define in DynamoDB table. Once successfully validated, we will send them for publishing. In here, the integration will be called to request the price change to the regional company system. When they return the response, we will display the result back to the user. We have been using Lambda for 1 year now. As a developer, I found there are quite a number of advantages. Firstly, it's easy to use. There's no need to manage the server. Lambda also helps you with auto-scaling. You only got charged for what you use. Moreover, Lambda supports multiple triggers. This allows you to have many options for your architecture. However, we did meet some challenges along the way. The first one is 1,000 concurrent invocation per account. This one can requested for increase, but still need to be taken into account when you design your architecture. The second limitation is 3 GB memory and 5 minutes timeout. If you have a memory intensive or time-consuming task, it's better for you to apply the master worker approach. Thirdly, sometimes Lambda cold start can take up to few seconds. To reduce this latency, we use the warm-up plugin, which triggers Lambda every 5 minutes so that it's ready for the next invocation. At some point, we also encounter some costs rising on DynamoDB because of the nature of our product. So as we didn't use Lambda trigger, we switched to RDS for some of the services. Lastly, there is one challenge that is true for Lambda, but more general for microservice architecture itself. It's the difficulty in checking and debugging. To resolve the issue, we implemented correction ID by passing a unique ID through different components for one event. That way we can check the event quite easily. So that's it for my sharing on our serverless journey. Thank you. I will pass you back to Arthi.
Awesome. Well done. Okay, thank you, Min. And that architecture's definitely come a long way since my scribblings on the window, I guess. Um, what we'll do next is we'll go over a few different common serverless architecture patterns, and we'll also apply them and try to use them to build out a real-world application. So let's start with the basic ones first. What you see on the left is an example of a file or an object arriving in an S3 bucket, which then triggers a Lambda function to process that file. Common use cases for this would be to periodically upload your application data into your data warehousing system. Or you probably receive files from other third parties, which you need to then parse and then upload it into your own systems. The second pattern here is common in message-based architectures. A publisher would post messages to a topic, which is simple notification service in this case, and then you would have a Lambda function, which would then process these messages. Just recently, we announced the support for subscription filter policies, which means you can be selective about the messages that your Lambda or the subscribers actually process, so they don't have to blindly get all the messages that are delivered to a topic. Now, both of these are asynchronous invocation modes. API Gateway is a service that allows you to build RESTful interfaces. You can have API Gateway trigger a Lambda function to handle all your API requests. Now, a slight variation to this would be to have API Gateway invoke step functions instead. Step functions are a great way to orchestrate Lambda functions. That is, they allow you to chain together Lambda functions and build in control flow logic. They're also great to streamline your Lambda code because you can offload things like common validations to the step service. For those of you who attended Datadog's talk right before lunch, I think they spoke about this during their talk. The difference of this compared to the first one is that this is an asynchronous invocation because when you have API Gateway invoke step functions, your client won't wait for a response. Now, what if you don't have a need to invoke Lambda functions at all? You can use API Gateway to proxy requests directly to backend AWS services like DynamoDB tables or Amazon S3. API Gateway here is a great way to decouple your AWS backend from the clients. It also gives you a lot of added benefits, for example, rate limiting or throttling, caching, and request validation. So let's pause here and look at how we can use some of these architecture patterns to build out a real-world application. So I'm going to switch over to my console now. Okay, great. What we have here is an example of a restaurant search application. So when a user logs in, the application shows me restaurants in the nearby area. So all these yellow markers you see here represent restaurants. So I can further drill down here and I can see what this restaurant here is. The bikes you see here are drivers who are currently probably delivering orders for their customers. So what I'm going to do now is, let's say I'm in a mood for pizza. So let me go type in pizza and see what happens. This application should return to me the nearest pizza place in this case. So now this website itself is a static website, which means I don't need a server to host this. The website is sitting in an S3 bucket right now. Of course, there are dynamic capabilities, like you saw when I searched for a particular cuisine type, it returned to me the nearest restaurant that serves it. So let's go to my developer tools here and see what happens exactly when I search for something. So let me go back and repeat my search here. And you should see that here's the request that got sent out. So my bucket actually invokes an API Gateway endpoint here. It calls the resource /restaurant/search and passes two parameters to it. One is the search terms I entered, and the second is my location coordinates. The API gateway, in turn, calls a Lambda function, and it is the Lambda function that's doing the actual work. So I'm going to switch to my AWS console here. And let's take a quick look at the Lambda function itself. So what you see at the very top here is Lambda's security configuration. So on the left here, you have the function policies, which tell you who is allowed to invoke your Lambda function. On the right here, you have the execution policies, which basically controls what other AWS services my Lambda function can talk to when it runs. So in this case, my Lambda function can talk to CloudWatch logs, so I can actually publish and view my logging information, and it can talk to two different databases. I'm using DynamoDB here to store basic information about my restaurants, and I'm indexing text-based fields into Elasticsearch, because Elasticsearch is great for both text and geospatial queries. So this pattern where you have a UI which happens to be a static website in S3, but it might as well be your native mobile app, invoking API gateway, which then calls Lambda, and Lambda talking to a data store, is a very typical serverless architecture pattern. So if we scroll down here and take a quick look at the Lambda code, in this case, the Lambda function is written in Node.js. You can see based on the parameters I pass to it, it executes an Elasticsearch query against my Elasticsearch cluster and returns the results. And finally, let's take a quick look at the monitoring tab here. And you should see that my Lambda function has just been invoked here. You can see how long it took my function to run, and good news, there are no errors. Now, the final point I want to make here is, although the website itself is hosted on an S3 bucket, I'm actually accessing it via a CloudFront distribution. Now, CloudFront distribution is a content delivery network, which is a great idea if you have geographically distributed customers, but it also gives you a lot of added security benefits. For example, in this case, my S3 bucket itself is not publicly accessible, and only the CloudFront user is allowed to access it. So let's quickly confirm that. So I'm just going to copy my bucket that's hosting the website. Going to switch to a new tab here. So if you go here, sure enough, I get an access denied exception. This is good. So what I'm going to do now is I'm going to go and revert the bucket policy and make my bucket publicly accessible. So the way I'm going to do that is, I have an IAM policy here, which basically gives the get object access or public read access to all of this bucket, and the star here means basically to the entire world. So I'm going to run this. I have a simple script here that will apply this bucket policy to my bucket. Once that script runs, I'm going to switch back here, and I'm going to reload this page, and I should see, sure enough, it loads my application now. I'll come back to the significance of what I just did a little later on in my talk. So great, I'm going to switch back to my slides now. Now you need a way to manage the users of your application. Amazon Cognito is a service that allows you to do that. Now what Cognito also does is it publishes these lifecycle events when a user registers for the first time or maybe changes their password. You can then have a Lambda function trigger to notify the user every time these events occur. For example, you can send out a welcome email to the user or let them know that they just reset their password. So while on the topic of emails, let's assume that you wish to run an email marketing campaign for your end users. Amazon SES, or Simple Email Service, acts as an outbound email server in this case. Now, occasionally, you might have emails bouncing, either because the user does not exist or maybe their mailbox is full. Now, over time, if you have too many bounces, then this can have a negative impact on your reputation. So one way to handle that would be to have a Lambda function look for these bounce emails. And you could have the Lambda go and update your user database and flag those users so that you don't continue to send emails till you have verified their email addresses. So let's look at how Lambda might help in the database world. The first diagram you see here is an example of implementing change data capture for the NoSQL database DynamoDB. So change data capture is just the process of logging all the changes to your database, typically with the intent of replicating your database elsewhere. So you can do that for DynamoDB by first enabling streams. DynamoDB streams are built on top of Kinesis streams. What that does is all changes that occur to your table are now written out to the stream. You can then have a Lambda function read these changes from the stream and maybe replicate the data to another DynamoDB in a different region, or it could probably just transform the data. It may just summarize the data and upload it into your data warehouse. What about a relational database context? Now, stored procedures in relational databases are just your business logic that reside within the database. They're typically executed in response to insert updates or deletes, or they can be directly invoked from your application code. Now, stored procedures can be computationally intensive, and they're also very closely coupled to your database engine. So if you're considering changing your database engine, it could involve a fair amount of rework to migrate them. However, with Amazon Aurora, which is a managed relational database service, you can now have Lambda as stored procedures. This not only reduces the load on your database, you now have far more flexibility with what you can do within a stored procedure. Of course, over time, as you collect data, you would want to analyze the data, maybe to draw customer insights. So I'm not going to dive much deep into data analytics in general, but I'd like to talk about how we can use streaming analytics for our restaurant app. So I'm going to switch back to my console again. Okay, so if you see here on my console, all the bikes here are slowly moving. So I don't actually have drivers on the streets of Singapore right now sending me heartbeats. So the way I'm doing this is I have a simple Python script running on my EC2 machine here. And it's the script that is simulating the movement of the drivers. So what I'm going to do is I am going to kill the script. And instead, I'm going to go ahead and run a slightly different script. And let's go and see what happens to the Lambda functions here. Oh, to the drivers here. Awesome. I call that the Lambda dance. So what really happened there was the script I ran went and updated the coordinates of my drivers in a DynamoDB table on which I have streams enabled. Now, what the Lambda function subscribed to the stream does is picks it up and indexes it into an Elasticsearch database. Well, that's great. That explains the backend flow of things. Now, for the changes to reflect on my UI, there are two ways to go about it. One, I can continuously poll my backend to pull the changes in, but that's really a bit wasteful if you really don't have any changes to pull. And the second and probably better way to do that is to have my backend push the changes out to me as and when they become available. So how are we doing that? So if I go to my WebSocket tab here, you will see that I have an MQTT WebSocket connection set up here. So WebSockets just allow a client and a server to have a two-way communication channel. And they're also a great way to have your server push the changes out to the UI. So hang on, Lambda is serverless, so how exactly are we doing this? So I'm using the service called AWS AppSync in order to do this. AppSync is just a managed GraphQL service, and in fact, you can see our GraphQL endpoint on this tab here. So GraphQL is just a data query API. It allows clients to specify queries in GraphQL syntax that needs to be run against backend data stores. It's typically used as an alternative to REST. So today, I'm not going to talk too much about AWS AppSync, but for those of you who are interested, I'll be happy to answer questions later after this call. So one of the practical applications of real-time streaming for a restaurant app would be dynamically updating the routes of the drivers. Based on your knowledge of their current position and maybe local traffic conditions, if you see that a particular road is blocked, you can notify the driver so that they reach their destination on time. And to complete our analytics story over time, as you collect data about your user and about restaurants, you may want to look at predictive analytics, where given a user profile and given a restaurant profile, you may want to train a machine learning algorithm that sort of tells you whether the user is likely to enjoy the particular restaurant or not. So in this case, I've just trained a simple model using Amazon machine learning in order to do that. That's great. I'm going to switch back to my slides now. Great. So all this while, we've been looking at Lambda mostly from a backend context, but what if you want to run this processing closer to your end users? So you can do that with Lambda at the edge, because Lambda integrates with CloudFront. There are really useful applications for Lambda at the edge. For example, you can improve the cacheability of your content by dynamically updating cache headers. You can rewrite URLs. You can dynamically generate content. But I'd like to specifically call out how one of our startup ISVs, DexSecure, are using this today. So they use Lambda at the edge in combination with their custom algorithms to dynamically optimize web assets that are served out of CloudFront distributions, which I think is really cool. So I'm going to switch gears here and focus on the last category of serverless applications, which is around IT automation. AWS Config is a service that keeps track of all the changes to your AWS infrastructure. And then you can configure it to publish a notification out to an SNS topic. So in my case, I've configured config to watch out for all publicly accessible S3 buckets in my account. And every time it spots one, it'll send out a notification to an SNS topic, and then I have a Lambda function that does two things. One, it notifies me on a Slack channel, and second, it'll undo the public read policy. Yeah? And a quick note I'd like to add is just end of last week, we announced that AWS Config can now publish these notifications to CloudWatch events. So you no longer need that SNS topic, and you can just have Lambda configured to listen to the CloudWatch events. So I'm going to quickly switch to my console here again. And let's take a look at what happened to the bucket I marked publicly accessible. So this is the S3 bucket, which I'm going to reload again. And you can see here that I get the access denied exception. What I also want to show is I want to go to my Slack channel here. So right now, you should see a message here in red, which basically says the S3 bucket policy allows public read access for this specific bucket. Once Lambda reverts the change, I should see a green message here letting me know that everything is cool, which hopefully should be coming in any second now. Great. So there you go. So once Lambda has reverted it, config triggers another notification, and then I get a message on my Slack saying all good now. This resource was non-compliant earlier. It is now compliant. Great. So I'm going to switch back to my slides again. So what else? You can think of CloudTrail as a sibling to config. So CloudTrail keeps track of all the API calls made against your AWS account, and it delivers a periodic report to an S3 bucket. You can then have Lambda process this report and either detect compliance violations, or it could optionally maybe log this data elsewhere into a data warehouse for maybe auditing purposes. So are there more architecture patterns? Yes, there are a lot more architecture patterns we did not have time to cover today. For example, CloudFormation is a service that allows you to automate the creation of your AWS infrastructure. You can use Lambda as a custom resource in CloudFormation templates, which allows you to make your CloudFormation templates dynamic. You can use Lambda as a managed cron and trigger it at periodic intervals, maybe to turn your dev and test environments on and off at scheduled times. You can use Lambda to analyze CloudWatch logs. Lambda also integrates very nicely with our code services. You can use Lambda within your CI/CD pipeline to stub interfaces, or maybe you could even run unit tests on it. As an aside, for those of you who are interested in understanding about CI/CD for serverless functions, I'd recommend you hang around for GitHub's talk after mine, where they'll be covering this. And finally, Lambda can be used with chatbots and also IoT. Again, for all you IoT fans in the audience, my colleague Tim will be delivering a talk later this evening. He has some really cool demos lined up, so watch out for that. So to conclude, really, you can think of Lambda as a Swiss Army knife. There are many different use cases and applications for it. And of all the architectures we discussed today, don't look at them in isolation. You can sort of, like we saw for the restaurant application, we can combine many different architecture patterns and really build out sophisticated architectures. So on that note, I'd like to thank you for your time. Don't forget to take the survey. Thanks.